Physics 2211, Lab 1, Constant Velocity. Let's go. So, the purpose of this lab is to showcase the properties of Newton's second law. We will be comparing the observed position of an object traveling at constant velocity using the tracker software to its predicted motion using a computational model called GlowScript. Alright, oh yeah, and obviously the object of choice is Lightning McQueen. Boom. Okay, so Newton's second law, what is it? The momentum principle. So, Newton's second law states that the external net force equals the system's change in momentum divided by the time over which it occurs, which is, bam, this equation. And a system with no net force acting upon it will furthermore have no change in momentum. What does this mean? Well, it's this equation right here. If the net force is 0, 0 times delta t is 0, so the momentum final equals the momentum initial. Furthermore, the velocity will be constant in a system with no net force acting upon it. What does this mean? Well, it's the same equation, but you divide everything by m, and the net force is still 0, so 0 divided by m times delta t is still 0, so the velocity final equals the velocity initial. The system in this case being Lightning McQueen, his surroundings are everything else, the hardwood floor, the slight air conditioning draft, etc. Alright, let's keep going. So the procedure, step 1, record Lightning McQueen zooming across the floor. Step 2, upload this video to tracker software. Step 3, track McQueen's position and time values using frame-by-frame analysis. This will serve as the observed position. Step 4, find the predicted position by developing a computational model on GlowScript by using the same initial velocity and position conditions. And finally, we'll graphically compare the observed and predicted positions. Okay, this is a video of Lightning McQueen using the tracker software. His real-time observed position. The purple lines serve as the coordinate axes, and this blue line serves as the calibration position. On the left side here, we have the t values, the 26 t values, and the 26 position values. All right. So, using the tracker analysis, we found that the total change in position was 0.657 meters, and the total change in time was 0.867 seconds. And since the average velocity equals the change in position over the change in time or the time it occurred, this change in position occurred, it would be 0.758 meters per second. And we see that the slope is relatively constant, so we can say that there's constant velocity. The average velocity equals the initial velocity, which equals the final velocity. All right, now let's look at a computational model. Boom. Okay, so we have the same graph, a bit straighter of a line, position versus time. How did we make this graph? Well, we have the initial position, ball position is 0, 0, 0, just like we had it before. The velocity is 0.758 since it's a constant velocity, and this is the velocity value that we just calculated right now. Since the video was in 30 frames per second, the delta t is 1 divided by 30 to make it a bit more accurate with each time step. The total time was 0.867 seconds, so that's why we have 0.867 here, because that's the length of time that we want to show the graph in. And then we know that the velocity is constant, so the ball velocity here is constant, and the ball position updates by adding the current ball position to the ball velocity times the delta t. Alright, let's go back. So, this is the graph. We have real-time position versus time and expected position versus time. What's the difference between these two graphs? Well, you can see it here. If you can't really see it, then right here we have a much straighter line in the expected position versus time, but the real-time position is a bit more wonky. It's not as straight. So why is this? Well, potential source of error, friction and air resistance serve as non-negligible forces. That means that the net force is not 0, which means that there isn't a constant velocity. So, or initial velocity does not equal final velocity. There also could have been tracking inaccuracy during the frame-by-frame analysis because I had to manually input the position of Lightning McQueen during each frame, so it might not have been completely accurate. There also could have just been a rounding error during the calculations, which would add slight deviation to the precise measurements in the software itself. Okay, addressing other questions. What if we flip the axes, like the positive x and negative x axes were changed? Well, there would be no change in the magnitude of slope, just the direction. So in this case, since we had a positive slope just now, it would be a negative slope if we change the axes. And can we determine how many forces are added together to give 0 net force in the case that you observe? Well, there's 3 different cases that I found. Case 1, if you choose a finite amount of surroundings, then yes, you have you know, for example, if it's just a hardwood floor, you know there's gravitational mg, but there's also a normal force up. So that's a finite amount of surroundings. But technically, there's an infinite amount of surroundings on a system, and infinity is not a countable number. So technically, in this case, no, there wouldn't be a finite amount of forces to find. And in the case 3, external forces like friction, it's not zero net force, so no. All right, thank you.